Hey everybody, this is Mr. Longo, and we are going to talk about the fundamental counting principle and permutations. And really what this is we're going to be reordering or coming up with different possible orders for different situations. So we're going to start out by going to dinner. And here's the thing. We have an Italian restaurant that has a great dinner deal where you get an appetizer, an entree, and a dessert for one low price. And it doesn't really matter. You can mix and match the meal any way you want. So I'm going to do your first example, and then you're going to do a second one. So at this place, you have two choices for your appetizer, bruschetta or toasted ravioli. For your entree, you have three choices. You can get the lasagna, the sausage and pepper platter, or spaghetti with meatballs. And then for dessert, you have two choices, either the cannoli or the tiramisu. So how many different meals can you make? Well, there's a couple of ways to do this. You could start this out by making a tree. Now, the tree would look a little along the lines of you have two choices for your appetizer. You have the bruschetta or you have the toasted ravioli. And then you have three choices for dinner. For each possible appetizer, you've got the lasagna, the sausage, or the spaghetti with meatballs. Same with the other one. And then each one of those gives you the option of a dessert, and it's either the cannoli or the tiramisu. Now, that's quite a bit of work just to list out different possible options. So there's a shortcut to that. And what you're doing is just thinking about how many appetizer choices you have times how many entree choices you have times how many dessert choices you have. So you have two appetizer choices, three entree choices, and two dessert choices. So 2 times 3 times 2 is going to end up giving you 12 different meals. Okay, so that's how many different ways you can organize your meal. Now again, you could just break it down with a tree, but that will take a while when you have a lot more options. Like the next example. So the next example, there's a different restaurant that has 7 appetizers, 13 entrees, and 2 different desserts. If you were to have every possible combination, how many weeks will it take if you ate there once a day? Now, this is going to be a little crazy, but I don't know if I would eat at the same place that many times in a row, but we're just going to pretend that you did. How many different weeks would you have to go eat at this restaurant to try every possible combination? So just see if you can figure it out. Click play when you're ready. So for this one, you had 7 appetizer choices times 13 different entree choices times 2 different dessert options. You should have came up with 182 different meals. So if there are 7 days in a week, then you would have to go eat for 26 weeks at this same place. Now, if it's really good food, then hey, that would be awesome. It cost you a lot of money, but it sounds like a good idea to me. But I think I'd get tired of the same restaurant, so I don't think I'd be doing it. All right, so that's an example of how you calculate different possibilities when you have different options, which takes us to the fundamental counting principle. And really, it's what we just did. If you have m ways, then there's n ways that something else can happen, and then there's p ways that something else can happen. You just multiply m times n times p. So let's talk about a license plate. How many different license plate orders are possible if the state requires it to have 3 digits followed by 3 letters? So a lot of times it's really helpful to kind of sketch out a little plan of what you're talking about. So it says that you have 3 different digits first. So you have a number, and another number. And then it's followed by 3 letters. So you have letter, letter, letter. So now let's just go talk about what our options are. Well, we have 10 different digits we can use, 0 through 9. And then for letters, we have A through Z, which we have 26 different options. Okay, so we would just multiply 10 times 10 times 10 times 26 times 26 times 26, and you would end up with over 17 million different license plate options. Now, of course, this is not taking into consideration any vanity plates or personalized plates, or once they run out of those combinations, adding a fourth letter or doing 2 digits and 4 letters. There's all sorts of different kinds. But for that specific layout, you have over 17 million options. So the next one is extremely similar, but there's one little twist, and that is you are not allowed to repeat anything. Okay, so you're not allowed to repeat any letters or any numbers. So think about that for a minute. Click pause, give it a shot, click play when you're ready. So very similar layout. You still have number, 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 letter, letter, letter. However, after you have 10 choices for the first number, you only have 9 choices for the second, and then 8 for the third. With our letters, we have 26 choices for the first letter, but since we can't repeat, we only have 25 for the second and 24 for the third letter. So it's very similar, but you just have to take into consideration that something has already happened. So that would give us 11,232,000 different combinations if we are going to use the letters without repeating and numbers without repeating as well. Okay? So the last one in this counting principle example is a password for a computer. Now there's very specific instructions. It has to be 5 characters, and the first entry must be a letter, and the last entry must be a number. Now for this particular example, we're going to assume that of course we have upper and lower case, but we're going to pretend you cannot use any symbols, no exclamation points or pound signs, nothing. Only letters and numbers. See if you can figure out how many different password options you have if you must follow these rules. Give it a shot. So for this one, you should have laid out 5 digits, and the first one has to be a letter. So if there's 26 letters, 26 capital, 26 lowercase, you would actually have 52 different choices for the first one. The last must be a number. 0 through 9 would give us 10 options. But then anything in the middle can be a letter or a number. So we actually have 62 options for the 3 middle characters. So that we would just multiply all of those together, and you would end up with 123,930,560 different passwords you can use just on 5 characters if you don't allow any symbols. So can you imagine how secure your password could be if you had 7 places with symbols allowed? And of course you can go calculate that now because now you know how. Okay, so that's our counting principle. Now we're going to switch over to permutations. Now permutations is when an order matters. So if you have an ordering of R objects from a total possible of N objects, where order and rank matter, the abbreviation is N permutate R. And we're going to show you the formula right here, which is N factorial over N minus R factorial. So now you're wondering what a factorial is. Well, factorial is just a shortcut to multiplying a whole bunch of different numbers. So N factorial would just be N times N minus 1 times N minus 2 all the way down till you get to 1. An example would be 5 factorial. 5 factorial is just 5 times 4 times 3 times 2 until you get down to 1. And if you just did multiply all of those, you would get 120. So you actually do have a factorial button on your calculator. it would just be 5. And then we would go press the math button, and we could scroll through the different math options. And once you get to probability, number 4 is factorial. So 5 factorial is, boom, 120, like we already did. So yeah, you can pretty easily do 5 factorial, but what if you had to do 27 factorial? That would take you a very long time to type in your calculator, so it's nice to know where the factorial button is. So remember, you just click math and then slide over to probability. That's also where you're going to find the N permutate R button, which we're going to use here in a minute. So we're going to go to the Kentucky Derby, and we know that there are 8 horses in the race. So how many different ways can these horses finish? So without doing a whole line of 8 different ones and saying 8 options for the first, 7 options for the second, we now know that we would just be multiplying. So this is just 8 horses factorial, which is how many times or how many different ways they can finish. Because you'd have 8 choices for the first one, and then after that first horse finishes, there's only 7 horses left in the race, so there's 7 for the second, all the way down to times 1. So that would give us 8, and then remember, it's math, slide over to probability, number 4 is your factorial, click enter, and you have 40,320 different ways to have these horses come in. But in horse racing, a lot of times it's just the top 3 that get recognized, like you finish first, second, and third. So how many different ways can they finish in first, second, or third? So you can think about this in terms of first place, second place, and third place. And we would have 8 choices for the first place, 7 for the second, and 6 for the third place winner. Now our calculator will just do that for us if you wanted to say there's 8 in the race. How many different ways can we permutate 3 horses? Now remember, we use permutation because the order matters. So again, if you go to math and slide over to probability, you will see we have an NPR option, which is 2. And then you just have to fill in. There's 8 possible, and we want to permutate just the first 3 that come in, and we get 336. Okay, so knowing how to use a permutation in the calculator is going to save you a lot of time when you have a whole bunch of numbers, or a whole bunch of different ways things can happen. So that one, of course, was pretty short. But what if we needed to do 15 players on a team, on a baseball team, and on a baseball team, 9 players bat? So how many different batting orders can you come up with? Well, you would have to do 15 times 14 times 13. Again, you would type in a whole bunch of stuff. So why don't you figure out how many different batting orders can be made with 15 players on a team if you can only bat 9? Pause it and give it a shot. So again, there's 15 players and you need to permutate 9 different batters. So you just have to use the permutation, but this time we have 15 total options and only 9 get to play at the same time. So 15 permutate 9 would give us a huge amount of options. We actually have over 1 billion options here. So we have 1,816,214,400 different ways to come up with a batting order. Now, of course, most of the time, a coach already knows what he's going to do. Usually one of your fastest players hits first. One of your strongest hitters bats fourth or third. So, of course, it's not like it's just that many different possibilities in terms of selection. But if we were to just say how many different ways, that would be it. The last one is what if we have repetition? So everything we've done so far, there's no ties or there's no repeats. So if you have repeats, it makes things a little bit more challenging. So for example, let's just look at pop. So if we had a capital letter and a lowercase letter for pop, and then of course O is lowercase as well, we have 6 different ways we can arrange it. Capital, lowercase, lowercase, pop, or what if we did lower, lower, capital for the capital P coming last? You would see we have 6 different ways. But what if everything was lower or uppercase? Then you would only have 3 options. You would just have pop, OPP, or PPO. There would only be 3 different ones. So when you have repetition, it is the formula of just however many factorial divided by repeats factorial. Okay? So the easiest way to show you this is in Mississippi. So in Mississippi, you would have to count 1, 2, 3, 4, 5, 6, 7. You'd have 11 different letters in Mississippi. So you would have 11 factorial, but now you have to take in consideration repeats. So we only have 1M, but we have 4 S's, and we have 4 I's, and we have 2 P's. So that means we would have to divide by 4 factorial for the S's, 4 factorial for the I's, and 2 factorial for the P's. And you can divide by 1 factorial for the M, but 1 times, it's all by himself, he's 1. Okay, so you would just have to type all of those individually, or you can type it all into your calculator. Yes, you can do 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. You can do that. But if you were to type it all out, 11 factorial would give you this guy over 4 factorial, and 2 factorial. And that would give you a total of 34,650 different ways to rearrange Mississippi because there are repeated options. All right, so again, another lengthy video. That's just what happens when you're dealing with probability. Anywho, this is Longo and I'm out. See you, bye.